Hello everyone. Today we'll talk about the solution to the problem maximum employees to be invited to a meeting. As you can see, this is a hard problem and I'm later going to scroll down to the solution. So the solution is pretty long, it wouldn't fit on the single screen. So don't get discouraged if you're trying to solve this problem to actually spend a bit of time on it, because it's not a fast thing to do. And in particular, because there are some hard problems where it's really hard to come up with the idea on how to solve it, or hard problems like this, where the idea is maybe not super trivial, but it's pretty easy to see what's actually happening once you start thinking about it for a bit. And then you have to implement it, and the things you have to implement are also not super overwhelming. There's just a lot of it, and you have to combine it into a solution. So if at any point you want to pause and try to figure out the rest yourself, or try to solve this problem yourself, feel free to do so. This is a nice problem to do it. This is not just a problem where there is a single observation that makes the problem trivial, or you see immediately how to do it, but the implementation is very hard. No, this is a very balanced problem, so let's get to solving it. We want to sit down our employees in such a way that everybody sits next to somebody, well, next to the one person who's their best friend. So one person can be the best friend of many people, but every person has only one best friend. That best friend cannot be that person. In general, that kind of graph is called a functional graph. It's called a functional graph because this graph is essentially like a function where the argument is a mathematical function, where the argument is our person and the result is their best friend. And functions, as you know, well, for a given argument, they have exactly one value. That's why it's called a functional graph, because there's a function that defines a best friend for every person. So first, let's see the image of how to actually sit them down. What can happen is, of course, that, and by the way, the table is circular. So what can happen is that we have a person, and that person is sitting next to their best friend, and they are that person's best friend. So that's a trivial, nice two-cycle, everything is good. Another trivial case is that A is sitting next to B, B next to C, C next to D, and so on, back to A. So if you have a large cycle, then everybody's happy because everybody has their best friend, let's say, to their right. So that's another trivial case. Now, in that second trivial case of the big cycle, notice that there is no way to break it up without making things blow up. We cannot sit anybody else at that table because the cycle is necessary to be correct. Everybody has to have their best friend, and their best friend is not the previous person, so they have to take their best friend and sit them down to the right of them. So that big cycle is just a possible solution with no changes that are possible. However, when we have two people who are each other's best friends, so a cycle of length 2, we have essentially an opposite situation. We can take any table which is not just a large cycle, and sit them between, so sit them in some place where there is no relation in either one or second direction of being best friends, and we get a larger seating arrangement. In particular, the simplest example is if we have a pair of two people and another pair of two people, they can sit all four of them on one table and everybody's happy, because everybody's sitting right next to their best friend, for whom they are their best friend. And that's still not the end of what we can do, because we can combine those two ideas, and when we have two people who are best friends to each other, then we can actually take a chain, a tentacle, that starts at somebody else. We follow their best friends until we reach one of the two people in our pair, and we can sit them together to the side of that person from the pair. And we can still do it one better. We can take the second person in the pair and take a tentacle that ends at that person and sit them together. So we have, let's say that maybe we have person 1 who's friends with person A, and we have friends that end at person 1, so we have, let's say, 5, 4, 3, 2, 1. Then we have person A, and then we have person B, C, D, E, and so on, such that person E's best friend is person D, D to C, C to B, B to A. A, of course, goes to 1, 1 goes to A, and again, 5 goes to 4, 4 to 3, 3 to 2, 2 to 1. So we have two people who are each other's best friend, and we have a tentacle ending at one of them, and we have a tentacle ending at another one of them, and still we can combine multiple such structures into one big circular table. So what do? We take the best of a single cycle and the sum of all the possible arrangements of a pair, and two tentacles, one per each member of the pair. Now you see why the implementation is so long, and the implementation we have over here. So let's go get right into it, because it's pretty long, though it's not that difficult programmistically. Let n be the size of our graph. So first we'll be calculating the single cycle. So we'll remember the best cycle. We'll have, of course, a set of seen vertices, and now for every vertex, if it's seen, we don't do anything. Otherwise, let's get the biggest cycle that we have. That biggest cycle, this is something that looks like a Greek letter rho. There is this famous Pollard's rho algorithm because it again operates on functional graphs, and it looks like a letter rho because a letter rho is something like this. So this is a cycle, and we start somewhere else, we reach some cycle, then we would spin on that cycle for infinity. So this is why this is like a letter rho. So we start at some position which might not be on a cycle, then we have all the nodes that we have visited in that current run, and we have the current node. So the current node, we start at the first node that we were at, we go through everything, just remembering what we visited, always going according to this favorite list. Now, of course, if at the end we have reached the node that we've seen, and that node is not one of the nodes in marked, so it's not a node that we've marked only during this run, this means that we actually have not reached a cycle, there is some other cycle or something, and we have just hit into it, but we've already calculated it, so we don't want to do anything in that case, so we just continue. Otherwise, let's calculate the length of that cycle. The length of that cycle is just the length of all the nodes that we've seen, but we have to remove this tail. This tail starts at node start. We have reached back to the cycle on node cur, so while start is not equal to cur, we go one step forward and remove one node from the cycle. Of course, we want to remember the best cycle. This is the first part, and now the second part for all the pairs. Finding pairs is trivial, so we'll be maintaining all the seen nodes again, and we go for every node. Node is a pair if we haven't seen it, and the favorite of its favorite is back to that node, add it to the pair, mark both nodes as seen. And now we want to have the reverse graph from the original graph, so we just calculate it, because we want to be able to go to those tentacles. Those tentacles have to end at a node that we are looking at a node from the pair, so you have to go backwards along that path. So that's why we need the backwards graph. Joint will be the length of all the joint lengths of those pair plus tentacle, so at every point we'll be adding to joint 2 for our pair plus the tentacle. And to calculate the tentacle, now this is trivial because this is just a simple BFS. So we take our node, we just have to make sure that when we have a pair of UV, then we don't investigate V as a start of a tentacle, because that would be illegal. V is already seated to the other side of the node U. And BFS, of course, we need a queue, so dec in Python. We go through all the neighbors in this reverse graph, skipping the parent, and adding them to the BFS queue. And so you have BFS queue, layer 1, we go through all the layers, so with this walrus operator, we remember the number of nodes in that layer, we eat all the nodes in the current layer, and we add nodes back to the queue. We actually don't have to check any visitations or anything because of the shape of this functional graph. After every layer we increase the number of the layer, at the end we just return the number of the layer. So in other words, we take one node from the pair, and we go through all the neighbors from that node, and again we step back, we want to find the longest tentacle. To joint we add 2, so for the pair, plus the longest tentacle at U, so we don't want to visit V, and another at V, we don't want to visit U. And finally, the final result is the maximum of the best cycle, so here at line 22, and the sum of all those found tentacly situations, which is just joint. And this is the final result and the final solution.